All right, I think it's probably a good time to get started. And what I'd like to do is begin. I'll introduce myself first. My name is David Lazell. I'm the Energy Systems Architect with the Transition Accelerator and also involved with the Edmonton Regional Hydrogen Hub. Hamid Ramanafard, who's going to be given the presentation today, is an energy systems analyst with the Transition Accelerator, and he's also working with the Edmonton Regional Hydrogen Hub, looking at opportunities for using hydrogen and deploying hydrogen within the Edmonton region and surrounding areas that would benefit the economy in the Edmonton region. As a chemical engineer, Hamid has focused on renewable energy, artificial intelligence, CO2 capture and sequestration, energy economics, and risk analysis. He has 10 years of experience in the energy industry, working mainly in research and development to decarbonize energy systems and assess different pathways to Canada's net zero future. Today, he's going to be talking about some work that he's been doing to explore the opportunity, the challenge, and the techno-economics a bit of making hydrogen from crude oil. And he's going to begin a presentation now, Hamid. We're going to have a presentation for about a half an hour, and then we'll open it up to questions. What I would ask people to do is to put your questions, if you would, into the Q&A box. We won't be able to, with the group we'll have, we won't be able to have raising hands and talking questions, but please put your questions into the question and answer box as they come up, and use the chat box to introduce yourself to other people who are on the webinar. Hamid, over to you. You can share your screen, please, and carry on.
Yeah, thanks, Dave, for the introduction. Let me share my screen. And so, do you see my screen?
Perfect.
Yeah, that's great. So, good morning, everyone. Of course, from Calgary, I am Hamid, and in today's webinar, I'm going to talk about the details of a recent study that we conducted about blue hydrogen production from the oil sands. In my presentation, I'm gonna first give a brief introduction, mentioning the motivation behind this study, the bitumen production technologies or methods that we considered in this study is the next part, and then I will talk about the options that we are proposing, the analysis that we did, the results, and finally I will go through the conclusions and the next steps. Okay, let's start. In 2019, Canada's GHG emissions was estimated to be about 738 megaton of CO2 equivalent per year, with around 28% from distributed combustion fuels such as gasoline, diesel, jet fuels, which are supporting the transportation across Canada. Given Canada's commitment to a net zero emission future by 2050, one of the sectors that should be decarbonized is the transportation sector. And the best solutions for decarbonizing the transportation sector is to find a new zero emissions energy carrier for replacing those traditional fossil fuels. And fortunately, as all of us are aware of, the solutions have been found for smaller cars. Those plug-in battery electric vehicles shows very good potentials to reduce the emissions. And for larger vehicles, on the other hand, hydrogen shows very promising potentials. Of course, by hydrogen, I mean the hydrogen that is produced with minimal GHG emissions. This hydrogen is converted to electricity using fuel cell technology, which then support the electrical drivetrain of the car. These types of cars are called hydrogen fuel cell vehicles, or HFCVs in brief, which are more efficient than the traditional ones, those with the internal combustion engines. And in comparison to battery electric vehicles, they have longer ranges with more rapid refueling time, which are attractive characteristics, especially for commercial sector. Now we understand what the problem is and what the solutions are. Let's imagine that we are in 2050 and the decarbonization of the transportation sector has been done successfully, which means that if we cannot say all vehicles, most of the vehicles are either electrified or they are using a zero emission energy carrier, such as hydrogen. So what I'd like to talk about is how this decarbonization impacts the oil industry at the global level and also at the provincial level with the focus in Alberta. So it is expected that the decarbonization of the transportation sector reduces the demand for the traditional fuels, which consequently undermine the demand for the oil. So the question here is, to what extent? On the energy basis, around 75% of a barrel of oil is converted to those traditional fuels, gasoline, diesel, and jet fuels in refineries. So it is reasonable to say that under a net zero emission scenario, around 70% of the oil demand will disappear. To get a clearer picture, here I brought the results of a study by International Energy Agency, IEA. In this study, it shows that the current production of the oil, or let's say the current demand for the oil, as there's a balance between the production and the demand, which is around 100 million barrels per day these days, is going to drop to around 30 million barrels per day under a net zero emission scenario. On the other hand, the price for oil, which is around $100 per barrel these days, is going to drop to around $25 per barrel, which is equivalent to around $4 per gigajoule, approximately the same as the natural gas prices these days. Of course, we need to take into account that this is Brent crude price. So we need to bring the difference between Brent crude and Western Texas Intermediate, and also the difference between Western Texas Intermediate and Western Canadian Select. So you now would admit that under a net zero emission scenario, producing oil from the oil sands resources here in Alberta might become economically feasible. We need also to add this point that most of the jurisdictions that are Alberta's trade partners, such as the US or even Canadian provinces such as British Columbia, they already approved the use of zero emission energy carrier in the near future. So under a net zero emission scenario, Alberta might be, there's a possibility that it cannot export those traditional fossil fuels to other jurisdictions, which worsens the situation. So the takeaway message here is that under a net zero emission scenario, the oil sands producers should find or produce alternatives from the oil sands in order to remain in the transportation market. And since hydrogen is part of the national and also provincial strategies for decarbonizing the energy system, so it can be considered, hydrogen can be considered a good option for producing from the oil sands. And because of that, the key questions that in this study we're trying to address is that if the oil sands producers can produce low carbon hydrogen from the oil sands, and we're trying to address this question from different perspectives. First of all, from the technical, let's say the production potentials, from the environmental in terms of the GHG emissions, and finally from the economic viewpoints. So yeah, in a couple of slides, I'm going to talk about the interesting results that we got by conducting this study. So bear with me. Okay, since in this study we considered an extension for the hydrogen production unit, an extension to an existing bitumen production facilities, we only consider two widely used, already commercialized and proven methods for producing bitumen from the oil sands resources. The first one is mining methods. This method is usually used for those oil sand deposits that are near to the surface, let's say 50 meters to 75 meters under the ground. In this method, as you can see here on the slide, so first of all, the oil sand is excavated through a shovel and truck operation. Thereafter, the excavated oil sand is hauled using those big haulers to the mining facility site, where it undergoes the hot water treatment process, and the bitumen is separated from the sands. The clean bitumen is then sent to an upgrader, and it is converted to synthetic crude oil, which is then sent to the refineries for producing those end-use fuels. So as I mentioned earlier, we're gonna consider an existing bitumen production facility with the mining methods here. We take the bitumen from here, instead of sending it to an upgrader followed by refineries for producing those end-use fuels, we take it and put it in a hydrogen production unit. I'm going to talk about the details of the process later on, and produce two separate pure streams of hydrogen, which can be used for local use or even export, and also carbon dioxide, which is going to be permanently sequestered in a geological storage. The second method is steam-assisted gravity drainage, or SAGD in brief. This method is usually used for those oil sand deposits that are deeper under the ground, let's say 150 meters to around 450 meters. So in this method, initially, two horizontal wells are drilled in the oil sand deposits, which are located 5 meters top from each other, approximately. Then the steam, which is generated through a steam generation unit, is injected through the injector well or the top well, which hits the bitumen, liquefies the bitumen, and then the bitumen gravity flows toward the production well. The water and bitumen are then sent or pumped to an oil-water separation unit where the bitumen is separated from the water, and then it is mixed with the diluent and produce the diluate stream, which is sent to the refineries for producing those traditional fossil fuels. Like the previous case, in this case, we take the clean bitumen from here, put it into a hydrogen production process that I'm going to talk about it later on to produce hydrogen and CO2. So considering these two methods, mining and SAGD, we are proposing 5 options for converting bitumen to the hydrogen. And the basis for all these options is the brownfield expansion of an existing bitumen production facility with the capacity of 10,000 barrels per day. Let's go and take a look at the options, the details of the options. The first option is called mine. As I mentioned earlier, the basis is 10,000 barrels per day. So the oil sands containing 10,000 barrels per day of bitumen is sent to a mining facility where we consider this mining facility business as usual case. So it uses diesel and grid electricity to, let's say, satisfy the energy demand. The clean bitumen is produced here, put it into a gasifier, followed by a water gas reactor and several step purification process, including pressure swing adsorption to produce hydrogen and CO2 streams. For the hydrogen production unit, the assumption that we made is that we can do carbon capture with an efficiency of 95%. Option number 2, which we call it mine H2 or mine hydrogen. So in this option, we thought that, okay, we capture the emissions from the hydrogen production unit. What are the strategies that we can, capture the emissions from here? In order to just reduce the emissions further. So for this purpose, we thought that it's a good idea to get some portions of hydrogen, of produced hydrogen, and thereafter put it into the mining facility to satisfy the demand for energy. So as you can see here, then the same as option number 1, the clean bitumen is produced, put into a gasifier, followed by a water gas reactor, and then several step purification process to produce hydrogen and CO2 storage. So the carbon capture efficiency that is considered for this option, same as option number 1, is 95%. Option number 3, which is SAGD, we call it, of course, SAGD option. Again, this is SAGD business as usual case, where the SAGD facility uses the natural gas and grid electricity, produce the clean bitumen. We put the bitumen into a gasification, followed by water gas ship and also purification process to produce hydrogen and also CO2 storage, and also CO2 for permanent storage. The assumption that we made, same as the previous assumptions, we consider the carbon capture efficiency of 95% for the hydrogen production unit, and for the SAGD facility, a steam to oil ratio of 2 is assumed. Option number 4, which we call it SAGD hydrogen. Again, we consider in this option to reduce the emissions from the bitumen production part as well. So for this purpose, same as mine H2, we consider using some portions of the produced hydrogen to satisfy the energy demand for the SAGD facility, produce the bitumen, put it into a gasifier, followed by a water gas reactor and purification process to produce hydrogen and CO2. Same assumptions have been made. So the carbon capture efficiency for the hydrogen production unit is assumed to be 95%, and the steam to oil ratio for SAGD facility is 2. And finally, option number 5, which we call it SAGD-Oxy. In this option, in order to reduce the emissions from the bitumen production facility, or let's say SAGD facility, instead of using some portions of the produced hydrogen, we consider using, or let's say producing some additional amount of oxygen. So in SAGD business as usual case, or option 3, we burn natural gas with air to generate the steam. This time we burn natural gas with oxygen to generate the steam, which increases the concentration of the CO2 in the flue gas of the steam generation unit. Therefore, it gives us this opportunity to have capture CO2 capture efficiency, higher CO2 capture efficiency. And for this option, we assume that we have CO2 capture efficiency of 95% for SAGD facility, in addition to the CO2 capture that we got for hydrogen production unit. And again, the steam to oil ratio of 2 is considered for this scenario. Okay, so just to summarize, we consider 5 options. So the difference between these options is about the way that we produce, or the methods that we deploy to produce bitumen, and also the strategy that we deploy for carbon management. In terms of the bitumen production, we consider 2 options for using mining methods and 2 options using SAGD. In terms of the carbon management strategy, the standard feature that we deploy for all options is to consider carbon capture with an efficiency of 95% for hydrogen production unit, while for bitumen production part, for two options, we consider using some portions of the produced hydrogen to mitigate the emissions from the production, bitumen production unit. And in the last case for SAGD, option number 5, we consider using burning natural gas with oxygen in order to reduce the GHG emission there. So now that we understand what the options are a little bit detailed, let's talk about the material and energy flows that we consider. Here in this slide, I just presented the block flow diagrams for energy and material flows of two options, mine option number 1 and SAGD option number 3. Of course, I'm not going to go through the details of these block flow diagrams. If you're interested or have any questions, just feel free to drop your question in Q&A, or also we can chat offline. Just the only thing is about the energy balances, we consider using maximum waste heat recovery here for satisfying the demand for the heat for gasifier and water gas heat reactor. If anything remains, we're going to use it in order to that waste heat to generate electricity. Okay, with that, let's move on to the results. First of all, let's talk about the production. So we define, the conversion efficiency as the energy content of the hydrogen that is produced per energy content of the bitumen that we put in. So as you can see here, for the 5 options, the conversion efficiency varies from around 61% for SAGD-H2, the worst option, to about 75% for SAGD, which is the best option. To get a better understanding here, I brought the efficiency that is reported for the reference case. I call hydrogen production from natural gas as the reference case in this presentation. So considering the reference case, we can see that for the top 3 options, SAGD, SAGD-Oxy, and mine, the estimated conversion efficiency is approximately comparable to the ones for the reference case. In terms of the production potential, you can see here that, again, the hydrogen production potential varies for the 5 options from around 29 kilogram of hydrogen per barrel of bitumen to about 35, 36 kilogram of hydrogen per barrel of bitumen for the base case, which is SAGD. Again, to get a better understanding here, because as I mentioned earlier, these are based on a 10,000 barrel per day of bitumen. So let's just assume that we have a typical SAGD facility with the capacity of 33,000 barrel per day. If we convert this facility to produce hydrogen, so from an oil producer facility to a hydrogen producer facility, what happened is that according to the number that we estimated here, this facility is able to produce around 1,200 ton of hydrogen per day, or to be precise, 1180 ton of hydrogen per day, which is equivalent to about 20% of current hydrogen production in Alberta. And of course, we need to take that into account that with this hydrogen production, there should be an amount of 6 megaton of CO2 per year for sequestration should be considered. So the takeaway message here is that under the national strategies and different reports, in near future, maybe we need a huge amount of hydrogen. So oil sand resources, our production analysis shows that can be considered as a good resource because of the abundant resources that we have in Alberta. So oil sand resources can be considered as a good resource for supporting that demand. Okay, with that, let's talk a little bit about the environmental assessment. So here we presented the life cycle CO2 emissions from the 5 options. The dark blue color represents the emissions from the bitumen production part, while the lighter blue presents the emissions from the hydrogen production part. So as you can see here, the life cycle CO2 emissions for all 5 options varies from around 5 grams CO2 per megajoule of hydrogen for the best case, which is -2, to about 15 grams CO2 per megajoule of hydrogen for the worst case, which is SAGD. Again, to get a better understanding, let's do the comparison of these numbers with the base case, which is hydrogen production from natural gas with the carbon capture efficiency of 95%. So all the 5 options have life cycle CO2 emissions lower than the one that we estimated for the natural gas. In addition to that, I thought that it's a good idea to bring here the threshold that is defined by Hydrogen Europe in order to consider the produced hydrogen as a low carbon hydrogen. So the threshold that they define is around 31 gram CO2 per megajoule of hydrogen. And as you can see here, again, the 5 options are lower than the defined threshold by Hydrogen Europe. So the takeaway message here is that the hydrogen that is produced from the oil sands have this potential, or has this potential to be considered or to be qualified as a low carbon hydrogen under a net zero emission scenario. Of course, one thing that needs to be taken into account, if we want to produce the hydrogen here in Alberta and thereafter export it to other jurisdictions, let's say Europe, so the delivery emissions should be considered. This is not considered in our calculation, the delivery emissions here. Okay, let's now talk about the economic analysis that we did. Because of the scarcity of the data, especially on the public domain, so we thought that instead of doing the economic analysis for all 5 options, let's first identify the best option, and then we do the economic analysis for the best option. For this purpose, we use Kepner and Tregoe, or in brief, KT analysis, where we, based on our in-house expertise, we define these 8 benchmarks: technology readiness level, commercial maturity, GHG emissions to data availability, and thereafter we assign an importance factor, to each of these benchmark, and then a weight factor for each options. We do the multiplication and the summation and estimated a score for each option. Of course, this is the normalized one, which varies from 0% to 100%. So you can see here that the best option, according to KT analysis, is SAGD. So we are doing the technical, the economic analysis for SAGD option. Here are the list of the assumptions that we made. First and most important thing, this is a preliminary economic analysis, and because of the uncertainty of the publicly available data, so we thought that instead of just putting a number there, we define a range. For this purpose, we define 2 scenarios, optimistic and conservative, and then we do the economic analysis for a brownfield expansion of a SAGD production, excuse me, facility with 10,000 barrels per day. The blue hydrogen production output is around 357 tons per day, with the CO2, let's say, for sequestration of around 5 kilotons per day. The other assumptions are, as follows. For the capital costs for the hydrogen production unit, we consider using the numbers by one of the NATL, one of the recent NATL studies in 2022. And for the SAGD capital cost, we consider the numbers that are provided by Alberta government for 2 SAGD facilities, of course, expansion projects for Christina Lake and also for Foster Creek project. In terms of the operating costs, we consider the lower range operating costs for Christina Lake and the upper range of operating costs for Foster Creek facility. The other assumptions are here. Again, if you have any questions, feel free to drop your question in QA session, and also we can chat offline about that. So let's go to the results. So based on the economic analysis that we did, we found out that the total installed capex of the whole process is about 2.4 to 3.9 billion Canadian dollars. With the total OPEX of 235 million to 340 million dollars. And finally, the levelized cost of hydrogen that is produced from the oil sand using SAGD as the bitumen production method is in the range of 3.5 to 5.4 dollar per kilogram of hydrogen. In order to get a better understanding in terms of the cost breakdown, so you can see here that the bar chart here, of course, this is for optimistic scenario. So in terms of the share of the capex and opex, they're approximately the same, with the capex of 49% and opex of 51% for the optimistic scenario. And thereafter, in terms of the cost breakdown for within the capex and within the opex, as you can see here, the hydrogen production unit has got the highest share with the 69% for capex and with 48% for the opex. For the conservative scenario, again, same results we see. In terms of the capex and opex share, approximately the same amount, with capex for 52% and opex with 48%. And in terms of the cost breakdown within the CapEx and OpEx, again, hydrogen production unit, like the optimistic scenario, has got the highest share. With that, let's move on to the conclusions and the next steps. So, conclusion. So we understood that under a net zero emission scenario, the oil sand producers should produce alternatives. And since hydrogen is part of our strategies, so one of the options that they can consider is to produce hydrogen. And this study is trying to see, or let's say to assess the hydrogen production from the oil sand from different perspectives. First of all, from the production potential. So you see that if you compare the typical SAGD facility to a hydrogen production facility, you can see that there is a potential to produce $1,000 to 1,200 tons of hydrogen per day, which is around 20% of the current hydrogen capacity in Alberta. And because of the abundance of oil sand resources, so we think that in terms of the production potential, so we receive a green light for hydrogen production from the oil sand. So definitely a viable option for, in terms of the production potential and meet the demand for hydrogen. In terms of the GHG intensity, because this is oil sands and they are highly emittive, so the biggest concern is about that in terms of the GHG emissions, they're not viable options. So as you saw that according to our estimations, the GHG emission intensity was estimated to be about 5 to 15 kilograms CO2 per gigajoule of hydrogen, which are lower than the threshold defined by Hydrogen Europe and also the blue gas, the emissions from blue hydrogen from the natural gas. So this means that the hydrogen produced from the oil sand can be considered as a low carbon hydrogen. So again, we receive a green light in terms of the environmental assessment here, and which shows that in terms of the environmental assessment, again, hydrogen production from the oil sands is feasible and viable. In terms of the economic analysis or economic assessment, the levelized cost of hydrogen was estimated to be around $3.5 to $5.4 per kilogram of hydrogen, which is a little bit high, and this might be too expensive. So I think that the main conclusion that one of the main conclusions that we can get here is that unless the capex and opex of the technologies for bitumen gasification to hydrogen are significantly reduced, we should say that, or this is the expectation, that the market for blue hydrogen production from the oil sands will be limited. Of course, there's a learning curve, and I think that in the next couple of decades, maybe there is a possibility that the capex and opex for bitumen gasification going to reduce significantly, and therefore, from the economic viewpoint, hydrogen production from the oil sands becomes viable. And in terms of the next steps, I think that the first and most scenario is to do a detailed techno-economic and environmental assessment using the numbers that are provided by the industry folks, or let's say those oil sand producers, and also the government support. And after doing that, based on the results of that detailed techno-economic assessment, I think that considering to run a demonstration or a pilot plant using, let's say, one of those gasifiers in the Long Lake for a short period of time can, clear things a lot. So based on that, I think that these are the first two options that need to be taken, and based on the results, we can move forward. And thank you so much for your attention. And back to you, Dave. Yeah.
Thank you very much. Maybe you can stop sharing if you don't mind, Hamid, and that'd be great. And we'll go through some questions if that's all right. I remind people to put your questions in the question and answer. Don't do the chat box if you don't mind. One of the first ones that they're asking here is was pyrolysis considered as an alternative to gasification? I mean, you might want to just mention some of the work you did on the ATP process, and we didn't present here, but I mean,
yeah, of course. So yeah, so one of the technologies that I think that they consider thermal cracking. So the technology behind the methane, or let's say the pyrolysis, is just thermal cracking. So we also consider that option, Alberta test process, which uses the thermal cracking in order to, let's say, produce lighter components, or let's say convert the bitumen to lighter component. But unfortunately, because of the scarcity of the data and thereafter the operational problems based on the previous experience, since that process hasn't been commercialized yet, so we did the analysis, but we thought that it's a good idea not to present it here. And instead of that, just stick to those already commercialized, proven technologies. So this is the main reason that we scope out the pyrolysis from our analysis here.
Right. Okay. Excellent. Thanks. Robert Lavoie is asking. He asked a bit about looking at natural gas for pyrolysis of natural gas to make carbon black and or graphite or something like that, plus hydrogen. Certainly that. I mean, maybe I'll just comment. We've certainly done quite a bit of looking at that, but that's not part of this project. This project was specifically looking at oil as the feedstocks.
Yeah.
So I think maybe the answer to that one is, and certainly there's a lot of interest in, we've been working with a number of companies that are trying to commercialize that technology.
Exactly, yeah.
What is the basis for the 95% CCS efficiency assumption? My understanding is that this is from Robert Bott, is that current CCS efficiency is generally closer to 90%. And how would lower efficiency affect the other projections? So do you want to comment on that?
Yeah, first of all, we are talking about gasification, and because of the higher concentration of CO2 in the gasifier, or let's say the output stream of the gasifier, so achieving those efficiency, I don't see any problem. So the recent NETL study for coal gasifications and producing hydrogen from that, assuming the carbon capture efficiency of 92 to 93%. So this is the main reason that we thought that it's a good idea to stick to that 95% of the carbon capture efficiency. Even if for natural gas, whenever the carbon dioxide concentration is not that much, right now with the, let's say, technologies, the new technologies that come to place, using, for example, autothermal reforming, those 95% can be achieved. And these are based on some of the studies by Jacobs. They already deployed that 95%. So we think that, yeah, that 95% is viable and it's feasible.
And certainly, I guess a comment on there is that a lot of the 90% is done when you're looking at post-combustion capture, right? If you're doing post-combustion capture technologies, where you've got a more dilute CO2 stream, you got to handle a lot more gas. Your 90% is perhaps more reasonable. Even that's sometimes hard to achieve. When we're talking about autothermal reforming in the case of methane from natural gas, or we're talking about gasification, I think the evidence is you can get higher CO2 and we can capture a higher percentage. And I think there's another question that relates to that with the 95% pushing and challenging that number. Now, if you didn't have the 95, how much higher would the emissions have been, right? In your various analysis would have been.
I don't think so. It's going to be just maybe a couple of percentage, but we can maybe run a sensitive analysis on that side just to address the concerns about that. But I don't expect that it's going to be that much, because let's say 5%, just to give you some understanding, 5% reduction in terms of the carbon capture efficiency reduces the, let's say, the amount of CO2 that needs to be sequestered about 2 kilotons per day. Okay, so for example, right now we are standing at 5.1. So let's say if reduces the carbon capture efficiency by 5% to 90%, thereafter the amount of CO2 that needs to be captured is 4.9. So only 2 kilotons per day. But in terms of the percentage, yeah, we need to do the calculation. Thanks for the comment. We'll see that if we're gonna try to address it through a sensitive analysis on that or not.
Oh, that sounds good. There's another question about the 95% efficiency. And maybe you missed comment. I mean, I think the Air Products out design for the Air Products facility, which is an autothermal reformer of methane, really comes in at about 95%
Yep.
efficiency. And they're even talking about using some of that hydrogen to generate the electricity for the compression for CCS and for the air separator. And I think that's the kind of, in a net zero future world where we're talking about, carbon pricing approaching $170 or higher per ton of CO2, the economics is quite strong to get as high a percentage as you can. And so I think, but it is technologies that have been deployed to show you can achieve it, but obviously not yet in Alberta. Is it maybe, okay, so maybe I may have missed this. Have you considered the cost of CCS in the effective price of the hydrogen that is produced? So what's involved in your calculations there? So maybe you want to,
Yep.
I don't know
So
if you want to show your pie charts or something, but I don't, but you could,
yeah,
you don't have to, maybe just describe it verbally.
yeah, let me just describe what I did. If it's necessary, I can reshare the slides. So the amount of, let's say the capital cost of the carbon capture is already included in the hydrogen production unit. So because for the gasification process, there's a unit that they call acid gas removal, or in brief AGR, which what it does is that it removes the acid gas and also the CO2 from that. And they use a select cell two-stage generator in order to do that. So it is already included in the hydrogen production unit there.
What about the geological storage and monitoring?
Yeah, so what we consider here, so this is for the capital cost, and in terms of the OPEX, what we consider is about the amount for piping, and let's say piping and then injecting, about that is 30 cents per kilogram of CO2. This is the amount that we consider in terms of the OPEX.
Oh, yeah, I thought it was $30 a ton.
Oh, yeah, sorry, yeah.
$30 a ton, yeah, $30 a ton, not 30 cents.
$30 a ton, but 30 cents per kilogram, yeah.
Okay. Okay, so how does the hydrogen output per unit of mined materials compare to hydrogen output per unit of natural gas? And what makes the bitumen clean? So we're talking about, so this is from Nabil Rahman. So how does hydrogen output per unit of mined material compare with the hydrogen output per unit of natural gas?
We defined per unit of natural gas. So I think that we can convert it based on the energy basis. So we talk about it later on. But sorry, we talked about it before, but here we only talk about in terms of the efficiency. So in terms of the amount of energy that we put in and the amount of energy in terms of the amount of energy that we get out of the process in terms of the hydrogen versus the amount of energy that we put in terms of the bitumen. And then for the natural gas, again, on the energy basis, the amount of energy in terms of the natural gas that you put in, and thereafter the amount of energy that you get in terms of the hydrogen out. So this is how we compare the result with each other. And of course, this is not an apple to apple or orange to orange comparison. We just want to show that, well, it is comparable to each other, and there is a potential for producing hydrogen from the ocean. This is fair things. In terms of the second part of your question, how we make bitumen clean. So exactly by putting it into a gasifier and thereafter do carbon capturing of the output stream of the gasification and water gas shift reactor, we try to capture the carbon, and this is how we make the output, the hydrogen clean by producing it from the ocean. I don't know if I making bitumen clean, you mean that one?
Well, I think, maybe certainly one of the things I think your results show is that it's the SAGD operation, of course, doesn't have the tailings ponds. And one of the advantages of this process that that is buried in some of your numbers is that the greenhouse gas, life cycle greenhouse gas emissions from making hydrogen from natural gas also includes a significant component of methane emissions from the natural gas recovery and transportation, et cetera. Whereas the actual upstream methane emissions are very low from the mining, from the oil sands operations, as long as you don't have the mine tailings, right? When you got the mine tailings, now you've got some significant methane emissions. And the SAGD process doesn't have tailings, doesn't use near the water, amounts of water, and have the land area impact. But you're putting the CO2 back underground, yeah. So maybe in a different location.
Dave, one thing to add is about that how to make the bitumen clean, especially for the mining side. We're not, there is not in the scope of this work to consider the methane emission from the tailing pond for the mining facilities. So this is one of the reasons that in that matrix that I showed for the in order to identify the best option for doing the economic analysis. This one of the benchmark and the criteria that we consider in our analysis. So yeah.
So one of the questions, I guess, comes back to the question of the market size for hydrogen potential. And so one of the questions here is, what if EVs take over the whole market for hydrogen fuel cell electric vehicles? And so essentially, is there going to be a market for hydrogen? So I know, in other parts of the transition, we've been doing a lot of analysis of where the market opportunity is. Maybe you can comment a bit on some of that work.
Yep, that's a good question. So all these, cases and scenarios that we need to take into account. One thing off the top of my head that I want to respond to that, okay, let's say, just imagine that EV is taking over all the market. So we need electricity. So then I think that on that side, hydrogen can be used in order to generate electricity if it is necessary. And if there is no market for, let's say, traditional fossil fuels, so we don't know what to do with the produced oil, we can convert them to the hydrogen and thereafter convert them to electricity. Of course, definitely, there's another question in terms of the efficiency and the amount of energy that is wasted here for all these conversions. But this can be considered as another option. But answering, that question, I think that this is sort of being the topic for another study, Dave. Is that right?
I think so. And maybe you should comment, because I know you're involved in this as well, Hamid. What about space heating in cold climates like Alberta or Saskatchewan, and one of the challenges in space heating, high seasonal electricity doesn't store very well.
Yeah,
right? And especially when you don't have, large hydro reservoirs to do it. And so,
yeah.
What's your analysis or the indication so far on the work you're doing on?
Sure.
On sort of hydrogen.
I think that all the concerns that we have with those EVs that, in addition to those, usage for space heatings, that I will admit that, especially for those climate, geographical areas such as Alberta. So is that, considering all the vehicles just convert to electricity to EVs, thereafter, in terms of the peak demand, we need to see that how it's going to, the whole grid system going to work with that, because, it's not a pattern lock. Everyone maybe just put it at the same time, and thereafter how we're going to deal with it. In addition to that, there are another usage for the hydrogen, especially for this cold climate area where the heat pumps, for now with the current technologies, are not working very well, especially during January and February here in Alberta, where the temperature reaches, let's say, lower than -20. So this is where I think that we can bring in hydrogen. Of course, by hydrogen, I don't mean hydrogen blending and this stuff. We bring in pure hydrogen, and let's say boilers or stoves or furnaces that are working with pure hydrogen to satisfy the energy demand with that. So this is another area that for hydrogen, in addition, to that can be considered. Yeah.
Excellent. One of the questions is compression of hydrogen, and I would add to that CO2, considered in the greenhouse gas cost analysis that you've been doing and on the life cycle. So the compression of hydrogen and CO2. I mean, how much compression of hydrogen is involved, and then have you included the compression of CO2 in your energy analysis for CO2 pipelines?
So what we consider here, of course, the compression, in terms of the pressure swing adsorption, the amount of energy that is required for separation is considered in our analysis. But in terms of the compressing of the CO2, since we assume that the hydrogen is coming out with the pressure of 25 bar, so this is the reason that we ignore that. But in terms of the amount of electricity that is required for the plant, we consider using some portions of hydrogen to satisfy that demand. And I think that if additional compression is required, let's say in order to put it in a pipeline, send it to somewhere else, so we can consider using some portions, very small amount, I think, in order to satisfy that demand for the compression. So for now, we just assume that the output of the pressure swing adsorption has enough pressure to send it for the local use, let's say for those fuel stations, for example.
So let's go back a bit to some of the things we talked about a little bit before, but there's a number of questions here and suggestions that maybe instead of taking bitumen and converting it into hydrogen and carbon dioxide and sequestering the carbon dioxide, we convert it into hydrogen and carbon black or some solid form of carbon, and then you don't have to do geological sequestration. You might have other applications, right? As graphene or graphite or whatever. Could you comment on the implications on that? I know maybe you don't have the precise numbers, but what would be the implications on the amount of hydrogen that would be produced per barrel of bitumen that you start with that?
Okay.
If there was a technology to make a carbon black out of hydrogen,
yes,
out of oil sands.
Yeah, before answering to that, I thought it's a good idea to talk about that the infrastructure here. One of the let's say, major benefits of doing it in Alberta, especially Alberta industrial heartland, or let's say within Edmonton region, Fort McMurray and these areas, is that the infrastructure for, let's say, transportation of the CO2 pipeline, and also the geological storage is ready there. So these are one of the benefits of Alberta, and this is exactly why we think that we need to go and move in that direction, because if we're not gonna, having or producing any CO2 thereafter, what's the use of those huge amount of investment that we did for those CO2 pipelines? So this is first things. And the second thing is about the carbon black market, because now the methane pyrolysis is just start rising, especially for the local uses, before the gates, and also for those stranded gases for indigenous people and all those purposes. So, and the carbon black market is pretty limited. So one concern that we have even considered methane pyrolysis and doing, bringing it at a scale in order to produce hydrogen, let's say for a community or for a fueling station like this. So what should we do with that carbon black? So that's a big question in order to deal with that. And because of that, we thought that it's a good idea just to stick to the CO2 right now and CO2 sequestration instead of just thinking about converting it to the carbon black. And also, of course, we have to do some analysis on that side, Dave, but in terms of the amount of energy that is required for doing that, and also the cost, because it is just adding the cost. As you saw that based on the current technologies, we are standing at around $2.4 to $3.9 billion in terms of the capital cost. So for sure, for such a study, I'm not looking for adding on anything and try to reduce it as much as possible to reduce the levelized cost. Yeah, I don't know if I was.
No, I think that's fine. I think it's great. Well, one of the questions is whether the slide deck will be available, and maybe you could actually, and certainly I think we're making available on the Transition Accelerator website. And I think it's also worth noting that we'll be releasing a pretty detailed report on this. We're just finalizing it. This webinar has held up a bit of the writing of the report, getting this ready. But I think that report will be, about a month from now, something like that. Yeah. Okay, so there'll be a report. It'll be available for download, free download on the Transition Accelerator and on the Edmonton Regional Hydrogen Hub websites. So that'll be available in a month or so. So one of the questions is, how is the cost of bitumen gasification compared to biomass gasification for hydrogen production? And you might comment on the NETL study that came out recently, and so biomass and bitumen gasification studies.
Yeah, for the biomass, unfortunately, I don't have any number off the top of my head. This is one of the projects that we're going to deal with it, and you're going to hear from Transition Accelerator, especially for those, Dave, if you want, of course, to talk about it, those waste materials to hydrogen. But if we consider coal, let's say, and assume it to be biomass, so with the same process for gold gasification, the number that is reported based on that NETL study is about 3 to 3.1 US dollar, and these are 2018, of course, US dollar. Per kilogram of hydrogen. This is the number that I have off the top of my head, but you can refer to that report for the levelized cost of hydrogen production from biomass, which I think that it's approximately the same. So 2.5 to 3.5, somewhere around that. But yeah, check that report. There's a number, good number there, which is pretty recent. It was released in April 2022, the report.
And I think one of the issues there is one of the factors, I guess, in biomass gasification, and I think in perhaps in bitumen gasification as well, is a question of perhaps first doing a pyrolysis stage, right, and to improve the efficiency and maybe the scale of your gasification. Pyrolysis followed by gasification. Certainly, some of the more promising biomass to hydrogen technologies involve a pyrolysis first and then a gasification stage.
Yeah.
So,
and yeah, another things is another things that needs to be taken into account is about the limits that we have in terms of the amount of available biomass that we can put it into gasification for hydrogen production. So again, in terms of the scale, I think that the biggest concern with that is that in terms of the scale, do we have that amount of biomass to have a sustainable, let's say, hydrogen production and continuous hydrogen production for the use or not? But in terms of the oil and resources, yeah, they're abundant there, and we're going to have it probably for next century, something like that. The oil and resources is there, yeah.
Right. So another question, did you consider CO2 transportation and CO2 storage site costs in your CCS analysis? And also, do you think there's enough storage site available for the amount of CO2 generated in the project? Maybe just a comment there, is we know that when you take methane and you convert it into hydrogen through a steam methane reforming or autothermal reforming, really what's dealing with is sequestering, say, if you're sequestering 95%, you're around between 9 to 9.5 kilograms of CO2 needs to be sequestered for every kilogram of hydrogen. And your numbers here was what, 14 to 16 or 17, depending on the process, kilograms of CO2. So obviously it's more. So do we have enough storage space and for this? And because you've got obviously a lot of CO2 has to be stored for every kilogram of hydrogen produced.
Yeah, in one of the TA's study, the amount of hydrogen required for the domestic use and also for the export is estimated to be around 120 kiloton of hydrogen per day. So yeah, if we want to consider that, well, let's just produce that hydrogen from the oil sands, definitely that sequestration is going to be the issue. But from my viewpoint, it's going to be a combination, of using natural gas, definitely, because this is the cheapest option. And if, of course, the cost for the gasification, bitumen gasification to hydrogen reduces and it becomes economically feasible. So we bring into account some portions of the produced hydrogen can be considered using oil sands. And in that case, yeah, let's say 1 to 3 plants of SAGD, typical SAGD facility plants can be considered to be converted for hydrogen production. In that case, yeah, I think that the capacity is in the range that we have at geological storage to sequester, that amount of CO2.
Okay, and the other part of that question, I think we almost answered before, was that the CO2 transportation and CO2 storage was included in your cost estimate.
Yeah. In terms of
$30 a ton, right?
Yeah, exactly. In terms of the capital cost, we already included that in the hydrogen production unit. And in terms of the operating costs, yeah, the transportation also injecting the CO2 under in the geological storage is already considered in our study.
Right. So have you studied process optimization of SAGD, SMR, CCS with water gas shifts? So optimizing the process and reforming as a key process range for constraints is a question from.
Yeah, so this is part of, for now we did of course, we did a high level, material and energy flows with that. So this is sort of being the next step, that if industry is interested, because we need accurate data in order to deal with that. Thereafter, I don't see any issues with doing, the optimization of the whole process. As you said, what we had said, you said bitumen production, SAGD, SMR?
Right. So I think they were talking about, or SAGD, SMR, CCS with water. So just optimizing, but it's hard to do a steam methane reforming with oil.
Yeah, exactly. Yeah. With the bitumen,
we haven't certainly done the optimization model.
Yeah,
we haven't done. We're far away from that. We need a lot more. This is pretty hard right now. One of the questions is interesting: is what is the Oil Sands Alliance Pathways Project? We think about this study, and have we talked to them? I don't know if you want to. I can respond to that because I have talked to them about it. Of course, the Oil Sands Alliance group is very interested in scope 1 and 2 emissions, and this is really solidly focused on scope 3 emissions. We have had some discussions and talked to some of the companies about this work. I think it's pretty far out, especially when you figure in oil sands companies are making $100 a barrel right now. This is not really not a credible strategy. I think our vision here is this is looking forward to a transition to a net zero energy future, where we really do actually start significantly undermining the market share for the products of oil sands production in the transportation sector. So, so that's, I don't know if you have any other comments on that. I mean, I think we're far out, I suppose, and whether the oil sands companies are actually thinking about this, maybe they are, maybe they're not. They're certainly not telling us about it. So. Fugitive emissions of natural gas processing or oil production from SAGD. We touched on this a little bit. So whether it's cold, what are the fugitive emissions and are they taken into account? So of the fugitive emissions for these processes.
Of course, we consider the fugitive emissions for estimating the life cycle CO2 emissions from the natural gas. But in terms of the SAGD facility, we only stick to the numbers that are reported by one of the Suncor's report for the SAGD facility and also one of the Jacobs study. So we calculated those fugitive emissions based on the, let's say, assuming SOR, estimate to oil ratio of 2, and doing that with that. So we just stick to those numbers that are reported by those engineering firms and also those companies. So we haven't done a detailed analysis on that. So we assume that the fugitive emissions is considered in their final numbers.
Right. So a couple of questions that actually just go and ask, challenge the underlying thought process around hydrogen here. One is it a waste to burn hydrogen in cars or for electricity generation to consume it in hydrogen where you could, you don't, maybe better to go with electric vehicles, I suppose, right? So maybe, that's one question as I read it. So does it make sense for hydrogen in cars or what about in trucks? What about trains, boats, ships, airplanes, off-road vehicles? Where's the role for hydrogen as a demand side?
So I think that, the larger the vehicle is, so definitely the role of the hydrogen becomes stronger. So we need to deploy them, of course, considering the current status of those battery electric vehicles. They're considering the weight of the batteries that should be, for example, in the airplane. I think that in an article, I just saw that it's going to be, let's say, several times of the weight of the airplane if we want to make the airplane as an electric, plane. So this is the main reason that hydrogen plays a very important role, in that, considering, of course, the current status of the technologies that we have. And then in terms of the ranges that we're talking about right now, battery electric vehicles still are within shorter ranges, especially in cold climate areas such as Alberta. There's lots of safety concerns that people will have, and in order to travel longer distances. We need to bring that into account, and also the refueling time, especially for the commercial sector. So what I'm thinking is that, for sure, for larger vehicles, for now, hydrogen is a better option.
Okay, I see it's 11:59. I know that this webinar channel is going to be used in 1 minute for now for another webinar that starts. So I must close this off now. Thank you very much. Thank you so much for the questions. Thanks to the audience, and we much appreciate your attendance, and feel free to contact us if you have any questions. I'm sorry I couldn't get through all of the questions. Thanks a lot. Thank you, Hamid.
Thank you so much. Yeah.